So we're going into the third chapter of the fourth section. Going to take a fast and sloppy tour through what's more or less the consensus of where life originated or how life originated. This is Dirk brings his family tree to class. Where up here, way up his family tree, you have the Jorgensens, Hilda and Ned, and the Olsons, Betty and Irv. And then Grandpa Bob, this guy was sucked into a tar pit. That's Grandpa, that's Bob. That's Grandma Rose. And then Uncle Andy had a tail, Dad and Mom, and then me and my sister. So, and also abbreviated look at the history of his life, or his family's life. So there's a lot of stuff to cover. And now that you're getting good at it, I'm going to have you mostly writing stuff down rather than putting too much stuff up here. I'll have overheads up here, but I won't be doing a lot of writing. And of course, you've got the book to look at as well. Thousands of years ago, what people knew of history, and I've talked about this before, what people knew of history is what other people told them. And how far back into the past could that go with an oral tradition? Is that it just kind of faded and faded and faded. So far as anybody knew, the world that existed pretty much matched the world that was. You know, wars and movements and stuff like that, but the world was the world. And so any attempt to explain where it came from had to kind of figure that it had just kind of started the way that it existed during their day. What I would call poof explanations, supernatural explanations, because how else do you get a complete world that looks the way the world around us looks? And so that's the basis for a lot of origin stories connected to all the world's religions, and there's a lot of them. Now, problem with a poof explanation isn't inherently that it's religious, it's that it's not testable. Is that the reason that science folks don't like the poof explanations is that you when you go, how do you test that? There is no way. And there actually is a quasi-scientific poof explanation that is just as frustrating. That's called panspermia. That's all one word. Widespread seeding is what panspermia means, like pandemic, widespread, epidemic. And the basic idea of panspermia is that when life started on Earth, it was already a step ahead. It was already prokaryote, bacterial life, which had been brought from somewhere else. Is that there's a possibility that bacteria can survive long periods of exposure to radiation and the nastiness of space, but this would have required millions and millions of years unless you buy into the aliens brought it here, intelligent aliens brought it here, which is a very small fringe subset of panspermia. But the problem with panspermia is you go, so it came from somewhere else. Okay, where else? We don't know. What were the conditions there like? We don't know. How did it get started there? We don't know. So there really isn't anything testable other than, can bacteria survive long periods of exposure to space? And since we're talking long enough to get from one star system to another, there's no way really to test that except in fairly short exposures. And in short exposures, they do relatively well. So then then people start to think, so if life started here, well, what did it look like at the beginning? And they immediately ran into what became known as the plant problem, Uniformitarianism, right? You investigate the past or great distances based on what you know happens in the present. And then you amend it if you find reasons to amend it. Well, people looked at the world around them, and the whole world was based on food chains where the producers at the bottom were photosynthetic. Convert light energy to chemical energy, fuels everything else. And so they said, well, then the first ecosystems had to have been based on photosynthesis because that's all we got. How do you get photosynthesis as a kind of a spontaneous, a spontaneous kind of eruption, kind of a poof for photosynthesis. And photosynthesis, as you already know, is a very complex process requiring a lot of very complex molecules. And converting from light energy to chemical energy is no easy thing to do. So it was that was kind of the roadblock for a really, really long time, is that unless you could explain where photosynthesis kind of arose spontaneously, you were kind of dead in the water. And then the astronomers were able to feed us some information. When we talked about photosynthesis, we talked about light energy, electromagnetic energy, and re-radiation, where certain atoms and molecules will absorb certain frequencies like tuning forks, like absorb certain frequencies of energy, pop some electrons out temporarily, unstable, they pop back down, but in the meantime, they've used and diffused a certain amount of energy, so they, to pop back down, release more electromagnetic energy, but it's a different frequency than what they absorbed. And it's a frequency signature for different materials. So you could look at light from a distant star, getting to us through stardust, and look at the frequencies and go, okay, there's a signature for oxygen, there's a signature for carbon dioxide, there's a signature for amino acids, there's a signature for methane, there's a signature for a whole slew of different organic materials that are in space dust. So now people started to rethink what the Earth first looked like when it first formed, right? First rocky and molten because of all the impacts, kind of spinning, heavy stuff settled toward the middle, that's why we have an iron core, lighter stuff settled toward the outside, silicas and other types of rocks, really light stuff settled around the gases. As it cooled, one of the gases, water vapor, cooled enough to precipitate down onto the surface, so it rained for, who knows, millions of years. Mixed with other light materials on the surface that were in the space dust of how we formed, and that was what's called primordial soup again. Primordial soup, where the first oceans were not oceans like what we have today. They were also chock full of organic molecules, little organic molecules. And then the question became, we're big organic molecules. Can you get from little ones to big ones? Fairly simply. What kind of energy do you need to throw at them in order to get them to merge together and become more complex organic molecules? And back in the 1950s, the Miller-Urey Experiment conducted, I'm pretty sure in Chicago, they took this big vat of what they thought at the time primordial soup looked like, or was composed of. They decided to supply a lightning energy input. So they put two electrodes in right above the surface of the liquid, and a spark jumped in between, and the electricity bled into the primordial soup that they set up. And so they had this pretty big vat that they ran for a couple of months. And when they analyzed the soup at the end, the little organic materials had become bigger organic materials. Not huge, but bigger. So it was a proof of concept sort of thing. Now, since then, we also have other types of evidence for primordial soup and for larger organic materials. Farther out in the solar system, where life, so far as we know, did not arise, you have a moon going around Saturn where it's covered with organic materials, so much so that it rains methane rain, it has methane rivers and methane lakes because it's cold, and the methane is liquefied at those low temperatures. Is it no really complex molecules that we can detect, but a whole system of primordial soup. It also turns out that there's primordial soup embedded in the crust of the Earth. When ocean hydrothermal vents crack and open up, the hot magma from underneath water goes in and comes up and erupts, but it also mixes with the remnants of the primordial soup underneath. So what comes up is a very rich organic mishmash that the organisms of those hydrothermal vents use to build molecules from. We'll come back to that. So we've got a starting point. And then the question becomes, so where do we go from here? Is that we want to get to life, but you're not going to get life, you're going to get steps. What do the steps have to be? Well, first we have to build larger, more complex molecules. Okay. They need to be able to take energy from the environment and organize themselves, or there has to be a system that allows them to organize. Self-organization, right? Big deal of life. Okay, that's one of the very first things that has to happen. Also, when you get molecules that are good at this, they need to be able to make copies of themselves. They need to be able to reproduce. Okay, so self-organization, use and transformation of energy, reproduction. All molecular stuff. And so the early levels of primordial soup would have been a big mishmash of molecules competing with each other for raw materials, possibly grabbing each other and pulling the raw materials out of competitor molecules, possibly banding together, producing complexes where one molecule is good at doing one thing and another molecule is good at doing other things and another molecule is good at something else. And over time, the successful ones flourish and the unsuccessful ones basically get broken down as bits and pieces. So, self-organization, use of energy, reproduction, evolution, change over time. And that's just for molecular complexes floating in this soup. Now, are the odds great for this happening? No, the odds are really horrible. Are the odds better if you consider you have an entire planet covered with this stuff, oceans covered with this stuff, and you have millions of years of cooking, and you have multiple sources of energy? You've got lightning, hot, very turbulent atmosphere, lots and lots. There's still a lot of lightning, like 1,000 lightning strikes a second on this planet still. Uniformitarianism. It was warmer. Remember Q10, is that as you make things warmer, reaction rates increase. And so you've got this huge massive soup for millions and millions of years cooking away and cooking away and cooking away. And so where do we go from there? And possibly what you get are things that if we could go back and look at them, we would go, these are essentially viruses, except they're not parasitic. Is that they're more independent entities. And I wonder if they aren't still in the oceans, we just don't know to look for them. Now this is an old overhead. The dates have changed. The dates keep changing on stuff. We do figure that about 4.5 billion years ago, you get the formation of the Earth in a recognizable form. So it's cooled enough to have oceans. The oldest prokaryotic fossils, that date keeps getting farther and farther and closer to this, depending on what you interpret in those ancient layers of rocks. You know, bacteria don't really fossilize, but they do leave clues. They leave chemical clues in the rocks. And sometimes also molecular clocks, although that's, when you're going back this far. I mean, I just saw an article that claimed that photosynthesis arose within a couple 100 million years of the cooling of the oceans based on extending a molecular clock backwards. Those clocks are iffy. The farther the distance you're gonna count the ticks, the more likely you are to be significantly off. But, you know, it's numbers. People love numbers. People trust numbers. I don't really trust that as a good. But there is evidence for the chemistry of bacteria, prokaryotic existence, within a couple 100 million years of the beginnings of the oceans themselves. So then the soup starts to run out. It's not renewable, right? It just precipitated onto the earth originally. It's a source of raw materials, but the more raw materials get integrated into complex materials, the less raw material there is around. And, you know, I'm sure pulling other molecules apart is a way to go. But at some point, the system needs to be goosed. You need producers at the bottom of a food chain to sustain it. Because remember, otherwise things just kind of fritter away as heat. The discovery of chemosynthesis, I've told you the story before, the discovery of ecosystems at these hydrothermal vents, so far down in the ocean that light doesn't reach them. And using the heat coming up from underneath as an energy source to slam molecules together and produce glucose. It's a much simpler process than using light to chemical energy conversion. That was a huge clue as to what the first recognizable living things would have looked like. I also skipped something. When you look at primordial soup, you also have these lipidish molecules that would have floated on the oceans, but in a turbulent, stormy situation would have been always driven underneath as bubbles. And asymmetrical molecules which spontaneously form bubbles with hydrophilic layers facing out and a hydrophobic layer in the middle. And all you really need is a situation where molecular complexes can grab and pull a bubble around it, keep it from floating back up to the surface and becoming more of the surface, just stabilize this fairly permeable but somewhat protective bubble around it as the first cell membranes. Phosphate would have been available. Phosphate would have been mixed in with these things. So you get from molecules. What molecules? Well, here we got a uniformitarian issue. We have protein-based chemistry, but we have DNA-based coding to make the proteins. Where the heck do you get that? That's actually the sticking point right now, is coming up with a logical progression to get that. The leading candidate right now is what they call the RNA World. I literally was just reading a web page about more of the RNA that people have discovered. Ribozymes is, I didn't realize until I read the article that ribozymes, which are RNA-based enzyme molecules, catalytic molecules, found mostly in viruses and prokaryotes. I didn't realize that until I read the article, but now being found in eukaryotes, including us, one that's pretty much unique just to hominids. So RNA can act like an enzyme. It can act like a protein. And being a nucleic acid, it can also act as a code. And so the assumption was that the first really functional systems were RNA-based, ones that could produce proteins to do the same job using some RNA as a code for the proteins, produced a more stable catalytic system and a more eventually DNA-based, more stable coding system, with RNA kind of still in the middle of that. That one, although on the surface it sounds reasonable, the biochemists trying to put together a logical step-by-step progression to this are not real close to doing that. So how do you test it? We're not anywhere near that. We don't really know where the basic functionality of our systems came from. So we're skipping a point as far as what we know. But now we're at bacteria. We are at bacteria that can use heat to produce glucose, and then bacteria that can take that from other bacteria, you know, bacterial predators and stuff. And so you have an ecosystem. Now we're going to get from that to photosynthesis. Oxygen produced as a byproduct of photosynthesis, remember. How do you get from simple chemosynthetic prokaryotes to photosynthetic prokaryotes? That was another sticking point. Until one day, two biologists are sorting through the critters that they were pulling off these hydrothermal vents, right? Ecosystems down there. So a lot of animals that were new to science. And sorting through the crustaceans and stuff, as one of them goes, they have eyes. Yeah. A lot of things down there have eyes. There's a lot of glowing stuff, you know, the fish have eyes. Yeah, but these guys crawl around on the bottom. Is that, what do they need eyes for? Is that energy would be better used after millions of years of evolution to do other things. They must be seeing something with those eyes that's useful to things that are on the bottom. And crawling up what they call the chimneys. The vents produce a lot of mineral-based chimneys and stuff. A lot of turbulence, a lot of heat. And a guy went, well, I don't know, maybe there is a source of light down there. Next trip down, they settle at the bottom near a hydrothermal vent, turn all the lights off, under a mile and a half of ocean, sitting there on the bottom with all of the lights turned off. I would think if you weren't claustrophobic, that would make you claustrophobic. But after 20 minutes or so of their lights their eyes getting used to it, they saw the vents glow. There's a chemistry in the vents that causes us very faint, but discernible to human eyes glow. And that's what the crabs and stuff were using. If they got in the wrong place and they got the turbulence tossed them away from the vents, which was their oasis of food, they could use their eyes to find their way back. Light detection becomes a critical component of life on a hydrothermal vent. Light detection is relatively simple chemistry. Chemosynthesis is relatively simple chemistry. Once you've got a way to pick the light up and use it in your detectors to do stuff, you've got a light to chemical conversion system, and you've got a heat to chemical conversion system. Now the theory is those two merged as photosynthesis. And since then, they've actually discovered that these vents do have photosynthetic organisms around them that use the light, the very dim light coming off of these vents as an energy source. So now we're to photosynthesis. Except if you're living off of the glow of a hydrothermal vent and the turbulence takes you up to the surface, you've gone from going through the dumpster to the buffet table. Lots of light up there. So photosynthesis may have started as a product of the glow of hydrothermal vents. It could very quickly spread to the whole surface of the planet where the oceans were. And we have a pretty good idea of when that happened because there are thousands of meters of rust in the fossil layers around this time. Metallic iron dissolves in water pretty well. Oxidized iron, rust, doesn't, precipitates out. So as more and more oxygen was released into the water, it tended to rust the iron and precipitate it out. And that's a pretty good indicator of when photosynthesis became a major player on the planet. And that happened about 2.5 billion years ago, so about 2 billion years in. Okay, we're gonna pause there.